In a diagrammatic form, the heat energy balance that we use when we talk about these drying processes, it looks like this on the right. There are essentially three things going on. Going from left to right, we have wet substance coming in, which is composed, as we see it, as fundamentally two components, the bone dry material and the total flow, of course the difference being water. We try to show that the bone dry materials into and out of the dryer is the same, and the difference is, of course, the moisture that we're driving off, and that moisture is being driven off by heat energy, which is being generated by the steam in this case, which is going from right to left, below, going through a heat exchanger, and then, of course, ambient air that's coming in from the bottom to the top, which is being driven through the process. The photograph is of this Norwegian district heat system, which has a hot water heat exchanger taking ambient air and then running it through this ID fan, and then that's driving the air pressure, which goes from below the mat, drives it through the material doing the drying. So these conditions, of course, vary greatly depending on what your ambient air temperature is, and there's a summer and winter sort of min-max situation that we have to consider when we size these things, and it can be quite a drain on the process. And that was a very big concern for our co-firing power plant. Next slide, please. We originally proposed this general arrangement here. The upper left diagram is of a truck dumper. The chips were all coming in from off-site preparation. As chips, they would come through the truck dumper. They would go through a screen. The overs of the screen would go through a hog so that we could reduce it to a nice uniform small size. This would go over to the upper right-hand side. That's a silo that would store about 3 or 4 days worth of chips on site. A screw in the bottom of that would reclaim the material and take it down to that rectangular box, which is a storage hopper. That would then take it to the dryer, which is that thing with the 3 smokestacks on it, or the exhaust stacks on it. The dry fiber would come out of that and go over to the far left side. That's a storage hopper, and then a distribution screw would distribute it to, in this case, 4 independent grinders. These grinders would have an overfeed system so that the overflow would go circulating back around. These grinders would grind the material, drop it into a pneumatic line, and that pneumatic line would take it into the boiler. So that was the original the concept, and of course the concerns and the energetics concerning the drying process were of great interest to the customer. They were eventually able to get a contract guaranteeing them that they would receive chips no greater than 30% moisture content, and so we have dropped the dryer from the project at this point, but they're moving ahead with the rest of it. Go ahead. In diagrammatic form, this is sort of what it looks like. A truck dumper there, you can see the screening and hogging tower, and then off to the silo, and then the dryer. And then you can see the bin and the grinders and the recirculation system there. Pretty simple, straightforward arrangement. We were fairly constrained in terms of the space that was present on the site. Go ahead. As an alternative example, I guess I wanted to throw this picture in. This is a wood-to-energy material handling system in a project in Germany in which they receive logs that have been harvested, left to dry in the woods. Then they're brought to the plant in a somewhat of a dry condition. They're, again, in the 30 to 35% moisture content range typically. They're then dropped onto this feed conveyor, goes through a chipper, and then you can see in the lower right-hand side, bins hold these chips inside the power plant. Then that material is used to feed the boiler. This is a 100% wood-fired boiler, in this case, not a co-fire operation. But in concept, there's no reason that you couldn't use this approach as well to provide the necessary flow for a co-fire operation if the fuel yard contained both coal and wood sources. Go ahead. This is another example of a fuel system that I wanted to just touch on. This is a pellet plant that has a wood-fired boiler. It's not a co-firing operation, but it's in the same realm. I mean, the wood that you see in the large circular pile on the left-hand side will be made into pellets and will eventually be used in a co-firing operation in Europe. The circular pile on the right-hand side is bark that comes from the log debarking operation that you see at the lower left. And that bark is then hogged and then goes into their boiler fuel feed system. Go ahead, next slide, please. This is a sort of a collage of photographs that show that installation. This is the one that has, if you look at the center left picture, the A-frame building with the door off of it and the opening, that's the boiler feed bin. So the conveyor that is feeding it has that bark that's coming from the reclaim area. Anyway, the dryers are located just behind it. I don't think you can quite see them, but the rapid thermal oxidation unit is there to the right of that photograph that shows the gas treatment system that's necessary. The fuel storage pile is the one on the bottom left, and you can see the sort of dark nature of that pile. This mill calls that the brownwood pile, and the upper picture, which is the wood, the debarked wood that's been chipped into microchips, that's their whitewood pile. So a very different way of terming these fundamentally different raw materials. Personally, I don't think bark is wood, but that's what they call it. Next slide, please. And that's mindful of my time. I think I've kept my time down to my 20 minutes, but that sort of shows an overview of a project that we're doing. That co-firing project that I've discussed is being installed and will probably be operating sometime in the very first part of 2012. So it's an interesting project. We're all watching it with great anticipation, and I think we have the material handling side of it pretty well organized. At least I hope I do.
It does seem so. Can we have questions from the floor? You mentioned the large amount of biofuels in the state of Washington. That always seems to be the big question is there going to be enough biofuels available for a particular project or in general? Do you want to address the question?
Yes. Well, I call you from, while I'm attending a biomass conference here in the state of Oregon. Seems like that's the growth industry these days is biomass conferences. But every conference has a major section having to do with fuel availability, distribution, transportation costs, distances, and quality. And that's an open question. With the level of harvesting that's occurring in states like Washington for timber, the harvest residues are fairly significant. I mean, tops, limbs, branches, and so forth, and the bark that's generated in log processing still represent a fairly substantial amount of biofuels that are available from what you might think of as traditional forestry-related sources if you include collection of the harvesting residues, which have been left in the forest. There's a lot of technologies now to go out there and get that and bring it in. Contracts are being written from fuel supply organizations for the biofuel plants that are well written and very, how do I want to say this? The fuel companies are required then to produce something in the neighborhood of 600,000 tons per year per biofuel plant, depending on its capacity. And these contracts seem to be viable. As I talk to the wood procurement people active in the state of Washington, they admit that they think that sort of fuel level is available. So the answer is yes. I think it could be done. There is that much is available, and that's not tapping so much sort of the municipal solid waste side, the green waste that comes from urban sources, and these are also available and are being used to the extent that they can, the fact that they're upgradable and cleanable. But yeah, I think there is a volume of biofuel available.
Other questions from the floor?
Yeah, Desmond, this is Jim Downey. I'm curious, why do they go through the step of pelletizing after they've chipped the wood?
Sure. Raw wood, as chipped, is got a couple of things going against it. One, it's usually half water, and its bulk density is relatively low. It's about 20 pounds per cubic foot as it sits there on the ground. But if you go through the pelletizing process, you drive the moisture out, and you need to do that in order to make pellets. And you densify it so that the resulting pellets that you produce are something like 43 to 44 pounds per cubic foot. So if you have to transport it any distance, you've given yourself a fourfold increase in the raw wood density. So at 20 pounds per cubic foot, you've got 10 pounds of wood and 10 pounds of water. You drive the water out, it would have been at 10 or 12 pounds per cubic foot. Now you pelletize it, it goes to 44. So literally you quadruple its wood basic density in the transportation. And that's really the reason. The second is when it gets to its final resting place. Let's imagine it's going to be industrial pellets for co-firing. You then simply grind the pellets back to a dust-like condition, similar to what I showed in those charts, which makes it directly injectable at that point. So essentially, by pelletizing them, the grinding process is pushed from the final user back to the producer, and it just makes the system work a lot better for the power plant.
Okay, good. I was always curious because it seemed like a wasted step to pelletize it and then regrind it again, but yeah, that makes sense. Thank you.
Other questions? Certainly one critical area is the ability to dry, first of all, getting the minimum moisture in the fuel and then drying the fuel without increasing the parasitic load in the system. And I know, this new Green Rivers, Great Energy Plant, rather, Great Rivers Energy Spiritwood is talking about a 66% efficient system using lignite, but using waste heat to dry the lignite, and then also using waste heat for the on-site ethanol plant. But if they go with cellulosic ethanol, they would be generating a large amount of biomass as well. So, you would have the perfect synergy of the waste heat going to the biomass, to the cellulosic ethanol plant, and considerable amounts of cellulosic waste coming back again. We had another speaker on here from DOE that said, if we met our cellulosic ethanol requirements, there'd be 100 million tons of waste biomass we'd have to do something with. So that could certainly add to the, appreciably to the amount of biomass that was available for direct combustion. So that certainly is. I guess one other thought I had here too is we've had presentations by Mitsubishi and Hitachi, who are inserting a gas-to-gas heat exchanger ahead of the electrostatic precipitator. And they're finding by taking the temperature down from 350 degrees or 325 degrees to 195 degrees prior to the precipitator, they're actually getting substantially increased performance out of it, and it eliminates the need to put a wet precipitator to meet this 10 milligrams per normal cubic meter requirement that Japan has. So, but what they're doing with that waste heat is trying to find, a good source of it. So it would seem, that we have two concepts here that could be married to improve the performance of the air pollution control equipment, and at the same time providing, the heat necessary to get the lower moisture in the wood. Does that seem to make sense, Desmond?
Yes, in fact, that's exactly the heat source we've been looking for, something that really doesn't cost them anything. If we can get that, the heat of the exhaust that they'd like to reduce anyway, and use that as our heat source for the drying on the front end, my God, that's the bonanza we've been looking for.
Yeah, well, we do have some presentations, and there's an amazing improvement in the efficiency of the precipitator just by by that reduction. And also just in total enthalpy and so forth. When you see this big steam plume going out of a FGD scrubber, you're looking at lots of wasted evaporating, heat going into evaporation there. So you got, 0.3 pounds of, or maybe even half a pound of water vapor per pound of dry gas going, at this 350 degrees, and cooling it back down again, you've eliminated quite a bit of water vapor. So, yeah, that's a lot of interesting synergies here. I think we just have to keep, viewing all these on a holistic basis and putting the advantages of lower pollution with lower parasitic energy for biofuels and marrying it all together. Any further comments for Desmond? Lots of good information, Desmond. Thanks.